Start.
Yeah, good evening, viewers. This is demo series 6. In demo series 5, you might have noticed who has watched this. So there actually it in fact abruptly finished, or discontinued also. This is because this was because of the fact that technical problem with the camera also, right? Now just from that point where we ended up, we will start that, right? And here you see that we were talking about the groundwater infiltration also, right? So we already discussed that for the estimation of sanitary sewage. So what you will do actually, first you find out the population, as I have told, the projected population. That means the after say 30 years or so design period, what will be the population also? By population projection also, that you have to project the population, and in the ultimate this sewage flow, that is to be found out, estimated based on the population, this projected population also. And then I'm not repeating this, just I'm summarizing based on the previous this demo series, the lecture session. So that actually you see that first is that you have to estimate the sanitary sewage first. So based on the ultimate population at the end of the design period, and then what will be the water supply, so that is to be multiplied by the water supply, and then you have to, as I have already mentioned or discussed also, that that is 40 to 90% of your this water supply, that actually we consider as the sewage coming from the, or resulting from the this sewerage system connected to the buildings like commercial or households, that is the residential buildings also. I'm not repeating that. So this actually to that, then 80% normally we usually we consider, and based on that we calculate that what is that, and to that actually we have to, depending on the population, we have to multiply this by peak factor also. This all are available in CPHO manual, that depending on the population, as the population, you remember, that increases, the peak factor that decreases. Why? Because you know that when the population is say 50,000, the peak factor say 3, right? While this that in the CPHO manual also you will see that when up to 20,000 or so, peak factor 1, and above 7,50,000 or so, so that is 2 or so, that is up to 20,000 3, and above 7 lakh, that means it is decreasing. Why? Because at a time simultaneously the possibility of getting the peak flow from the entire population, huge population suppose, so that will be lesser compared to the the population, the lesser number of population also, right? So suppose you have got 50,000, so naturally the peak factor will be more, up to 20,000 as it is given CPHO manual, the figures you will get. But the concept I'm telling you, that when the population is less, that probability or possibility of getting peak this flow or discharge, right? So that would be more, and vice versa. That means when the population will be very high, then in that case the peak factor will be less than that. Because of that, that simultaneously from the entire this range of population or so, the peak getting peak discharge, that would be lesser. So that is why this is taken like that. And the peak factor, why it is coming, already discussed also, peak factor. So what we do actually, that you know that the average water supply, based on that we consider, that means the projected population, if we write like that, the projected population, right, into water supply rate per capita, right, into that 40 to 90%. So let us take 80% or so. So that would be the the ultimate the sewage flow, and this water supply rate actually that is the average rate. Say if we take 135 or 150 LPCD, so that will be the average, remember. So that is why when the sewage, this estimation of sanitary sewage that is coming, we have to design the sewer line or the sewerage system for the peak discharge. So that is why we consider, or we take this factor into consideration to get the peak discharge based on the average flow. So average flow into that, so we have to multiply further, that is say peak factor, if we write like that, peak factor. So that will be the ultimate peak discharge, say. There is no such abbreviation called here I am giving, because so that you can understand that ultimate peak discharge or so. So that actually is calculated based on that. To that you have to add in worst condition what would be the groundwater infiltration. As I have already told that this actually will be depending on that the workmanship, quality of workmanship, while laying of that sewer line also, how much, to what extent the leakage could be prevented or could be minimized also based on that, and also the groundwater this position also, groundwater this one above sewer line or below sewer line, depending on that. So this actually is in CPHU manual. I have already discussed this, so accordingly you have to take this one. But remember that modern construction aids or so, that minimum and quality and standards of the workmanship or laying of the pipeline also, that is that could be minimized, that is taken minimized. But that does not mean that the sewerage, this system, the relaxation for the water tightness, that would be there. In no case the relaxation is to be permitted also, to be allowed. So water tightness, the test as per IS code also or CPHO manual, that has to be conducted, and that has to be complied with, while considering that the pipe sewer lines or so, this actually is watertight as much as possible, or maximum water tightness could be achieved by good laying, then jointing, and other workmanship also, so that could be done. So you add groundwater infiltration accordingly, and this actually is added to find out the total this sewage flow for which this is designed. Design part I am not discussing here, because this is quite a few lectures will be required for that. So we will be dealing with this full design of the sewerage system, both sanitary sewerage system as well as the storm drainage works also. That will be we will be taking up, will be these issues, this particular chapter we will discuss later. Okay, so this is about the sanitary sewage, and the velocity should be there enough, this one, so that this minimum 0.6 meter per second of the velocity should be ensured also while designing the sewerage system. Okay, and for ultimate peak flow, this is for the present peak flow, and for ultimate peak flow, that should be actually, this is 0.8 meter per second. That is to be ensured. But remember that when the laterals are there here, many a time during initial period also, that may not be, or that cannot be maintained also. So what we do actually, time to time flushing, because there is a minimum diameter also. Now for minimum diameter, usually we take 100 and minimum swell diameter. That means the pipe diameter also. So that is 150 millimeter or so. Many a time this is taken as 100 millimeter or so, but usually this. And for hilly areas, 100 millimeter is the minimum size it is maintained. So this actually, while doing that, if you see that this the velocity which is resulted by having this the pipe diameter also, in that case actually if it is less than that, then minimum you have to provide, right? But in that case, time to time flushing that would be there. Okay, number one point. Number two is that many a time in some lines, intermediate lines also, that may not be, marginally that may be less also. So in that case we assume or we consider that when the peak flow would be there, that would be flushed out. And in this connection, let me say that when the average that one will be there, we design for the peak discharge also, right? And peak during peak discharge also, flushing that will be required to sort of prevent or to flush out the deposition also. So when the velocity, normally the minimum flow in minimum sewage flow also, sewage flow, that actually is taken as 1/2 to 1/3 of average flow. Now sometimes the minimum flow also will come, and that time the deposition will take place. So if we draw that one here, say, so the deposition, let me find it. So here, if you come here, then for the minimum, this one, minimum during minimum flow also, there may be deposition, right? So this is actually, you see that this is the sewage storm. So let me take this one. So this is, suppose deposition may take place here, deposition of sludge, right? Because resulting from the velocity being lesser than 0.6 or sometimes 0.3 meter per second, in which situation actually that may deposit. But when the peak flow will come, that will be flushed out also, right? So that is normally we consider, and as I have told that for initial period, for laterals, the starting point also, that flushing, frequent flushing or time to time periodic flushing of this sewer line that may be required. Okay, so that is about this estimation of sanitary sewage also. Now let us now come to that, that storm flow. Okay, a storm flow. So if we take this storm flow, now in this connection, let me now itself give that the IS code number, because later on I may forget also, right? So IS code, what you may consult with. So that I am just erasing this one, because this already explained, right? So this also we have explained. N is the Manning's rugosity or roughness coefficient. R is the hydraulic radius, that I think I have discussed, weighted area by weighted perimeter. S is the hydraulic gradient also, that also I have discussed. So what you will do actually, that once you choose the diameter, then for that diameter, and minimum to be this one, any diameter when you choose, then gradient, you see that the gradient that would be there. This is the pipeline, say. Now if you know that this is one gradient, but if the gradient is flat more or less, here S will be less, here S will be more, hydraulic gradient. And here hydraulic gradient, as it is gravity flow, more or less the pipe gradient will be equal to the hydraulic gradient also. So this actually S will be here more, here it is less. So velocity to be resulted from such this steeper slope or so, that would be more. This say V1 and this is V2, so V1 will be greater than V2 or so because of the increased slope, steeper slope. Okay, this is one way you can do, and N, as you have seen, that this is, if it is more, then velocity will be less. In case of Manning's equation, I will discuss in more details when we will take up the design, and full design we will work out, and we will, for your practice also, this would be very much helpful for you, those who will be taking this course. You know that the full design we will discuss in more details. So this Manning's rugosity coefficient, as the pipe gets older also, or different kinds of pipes have got different rugosity coefficient, Manning's rugosity coefficient, and in that case actually depending on the, as it gets old or so, then this value will be more and more for Manning's equation. So as a result, that for old pipe also the V value will be lesser, remember. And here the frictional loss will be, more here because of the erosion. Also old pipe will have erosion, eroded this inner surface also, so because of that. So I'm not going further. So this actually we will have to consider. Now accordingly we have to estimate the sanitary sewage, and finally we have to design this one. Now what I was trying to say, that this actually the references, major references, if you can note down, that is, one is that CPHO. I have explained already CPHO manual, and where from you can get freely download this one, CPHO manuals. And also I have told that these manuals are for water supply, for sewerage and wastewater treatment, and also for solid waste management also. So CPHO manual, IS codes, and various IS codes will be could be used and to be consulted with. And say one for that manhole, if we give series of IS codes are there. So for manhole, suppose IS 4111 part 1. So that is the IS code, and also 1172 already discussed, how to find out the flow and all. And third one is that AAC, American Society of Civil Engineers, that is, and Water Environment Federation. So they give their the design and construction, so that also could be followed. That is for the international, work also. Many of you may work for international agencies where CPHO manual may not be, accepted. May not be accepted. Suppose you are doing a work in or for Thailand or Malaysia or elsewhere outside India. So in that case, CPHO manual, they don't understand CPHO manual. They understand in the sense that they do not accept that. Similarly, they, for the same reason, they do not accept that IS codes also, because this is applicable for Indian this situation, in India only, right? ISO is the international standard, right? So that actually could be always followed, ISO also. AC, this is also considered as the international this manual also, or reference, which you can follow for other area, unless otherwise specified, because every country or every zone or region, you can say that there may be a sort of separate manuals. For UK, say UK, this actually 1 2 3, this is anyway, this is 1 2 3 4, this is BS, British Standards, EN Environment 752, that is 2008 or so. That does not matter much, but the latest one to be followed, that is the drain and sewer system outside building. Okay, and this actually ASC, this is design and construction of sewerage system. So these are all about the references also. In case of that now let me erase this, rub out this to have the second type of the sewerage system, that is we call it distribution of storm water, that means coming from rain. As you know that when the rain falls, rain is the mother source, as you know. So depending on the characteristics of the ground or the land where the rain is falling, right, on, that actually part of that will be discharging, will be coming as runoff, and while the remaining part will be percolating through the ground. So this is this will add to the ground water also. So one part rain is the mother source. So depending on the here the perviousness or imperviousness, both way you can, either way you can define this. So if it is more pervious, then less runoff will be there. This side the percolation will be more. Clear this one? So and vice versa. If suppose the imperviousness is more for this ground, say the ground is the concrete, say, or say brick, this soiling, or other types of ground, because the soil characteristic, this may be very, very hard. So for hard soil also, where the clay content is more also, in that case actually, as you understand, as you know, that from soil mechanics also, the percolation, right, or penetration through soil will be more than the clay, right? So depending on the soil, this characteristics also, runoff, that will be decided, and similarly this groundwater flow, that how much that would be decided. So what we do actually for storm water, we have to consider that rain, that is the rainfall, right? So let us say rainfall, this. So rainfall, runoff, this characteristics, or that will be there. Okay. So here, the runoff reaching the storm sewer also, so is dependent on the, I am erasing this one. I think you have understood this, because this is not difficult to understand. Now this is dependent on intensity. Number one is the intensity and say duration of rainfall. Okay. Then characteristics of the tributary area. This tributary area, as I think I have told, the tributary area, depending on the topography, then that the political boundaries also, topographies, type of buildings, depending on that actually, the one particular, this one, say this is collecting from this many building, right? So this is cluster, will contribute the storm water after rainfall occurs also to this laterals also, right? So these are, of course, this was drawn for the sanitary sewage, but more or less same for this, okay, for the storm drainage system also. So characteristic of tributary area and the time required for such flow to reach the sewer. I will explain this one. The time required for storm flow to reach storm sewer. Right? And this actually these are the basic, parameters on which the storm, this runoff, that depends. Okay. Now intensity and duration, that means if intensity of rainfall, which is expressed in, in millimeter, usually millimeter per hour. Duration is say hour, or sometimes H also written, right? So intensity, if it is more, then your, the runoff will be more. Duration, if of rainfall, if it is more, then also the runoff will be more. Characteristics of the tributary area, what I have already discussed, that if it is pervious, then less runoff. If it is impervious, then more runoff also. Time required for the storm flow to reach storm sewer or so. So here actually you have to understand a little bit. Okay. So this I am erasing this one because this is the for storm. This one it may be directly discharged into the nearby river or so, or sometimes STP also, if STP has got the capacity, or if it is allowed to be received by the STP also. So this I am not, more or less many are overlapping also, many are common, so I am not discussing this one here. Now suppose this is sort of a section of storm drain, right? This is a section. Now here, suppose this area, this area is contributing this here. Now from the farthest end, what would be the time required to reach the once the rainfall occurs over this area, the runoff will be resulted, storm runoff, and that actually will take some time to reach the sewer line. Suppose this is the manhole, so this is one manhole, say if I draw like that, so this will be, this is this, so this is the longitudinal, or you can say the cross section also here. Similarly here also that would be there, manhole. Now this actually will enter into that manhole, that is this pipe, this one here, storm drain. This will be time of inflow, that is Ti, that is time of inflow. That means from the farthest end, how much time it is required for the storm, this flow, to reach the manhole, nearest manhole also. So that is actually Ti. And this actually to travel from this manhole to this manhole, suppose this is upstream manhole, from this manhole the flow is taking place to the other one, right? So here time of flow, that would be there. So this is the time of flow, right? So this actually time of concentration, what we term, this is time of concentration, is Ti plus Tf also, right? So when the rainfall, duration of rainfall is equal to the time of concentration for a particular this section, then the runoff will be maximum also. Today for this particular discussion we will we will go up to this only. Later on, when we will design what is the use of this time of concentration and other things actually, so that we will be discussing also. So I am here cutting short because that actually again will take a few lectures to complete the full design of a storm drainage system also. right? So time is important, characteristics is important of the tributary areas also. That means this characteristic, suppose here, what is the soil characteristic, what is the topography, and other factors also, vegetation and all, that will decide that what will be the its ultimate effective perviousness also, and intensity and duration of rainfall also, that also will be there. So to this extent, about this actually we will have this one here. Now what we do actually in that one, okay, runoff coefficient you will get for different types or shapes of the area. So that would be in manual. I will discuss this later when we will be talking about the design in more details. Okay. Then I mean hydraulics of flow, that is there, right? Okay, that already discussed. Now the rational method, there are some methods, you know, to calculate the storm this runoff also. So that actually, let me erase this, because this is related to the sewerage system, the sanitary sewerage system also. So here, then next will be here. So that way it will go towards the downstream end also. So say this is section 1, section 2, that way you can have, and these maybe that another line suppose is joining from this, right? So suppose this is 3 or whatever designation, or whatever way you define this, different sections also. So accordingly you have to design this. Okay, and you see that this is the methods for estimation of the this sanitary storm drainage system, or storm drain, the storm water also. So that actually will be, you know, that number 1 is the rational method. These methods, what I am writing down. So these methods are used to estimate the storm water also, right? Rational, this one. Then hydrograph method. Third one is the rainfall runoff correlation, established correlation, if it is there at all in some for some areas also. Fourth one is the digital computer model. And sometimes you know that the empirical formula also, empirical formula, and this actually is applicable for that particular case for which actually the empirical formula, a particular empirical formula has been developed. So these are the methods. Usually we use this rational method, usually, where this just today I am saying that the equation which actually governing equation which follows rational method, under rational method. So this would be Q is equal to 10 C I A. That means Q is that is the storm runoff which you are going to estimate, right? That is in meter cube per hour, storm runoff, which is resulted when the rainfall occurs. 10 is that for the units, this adjustment also, that is there. C is the coefficient of runoff. I is the intensity of rainfall. And A is the area contributing to the storm flow also. Which area? If area is big, naturally the Q will be more also. here one thing I just should tell, that intensity of rainfall usually, if it is more, then Q will be more, of course. But if the time of the duration of the rainfall, which actually will decide that what will be the impervious this one. If it's long duration rainfall also, in that case initially a particular area may have higher the C value coefficient of runoff also, initially higher. But initially you can say lower. That means the percolation will be more and the runoff will be less. But as the rainfall continues also, then the area will be saturated. Then the percolation will be less and the runoff will be more. So that also correlation. But details we will be discussing in the design when we will discuss the design. Then that would be more clear also. Right. So 10 CI, Q is equal to 10 CIA. So that is, used for estimation of the storm flow. Okay. Now, one more point only I will discuss, and remaining part that will be discussed in more details when we will discuss the design or the detailing of this. Now here you see that when you have got, for while designing a storm drainage system also for a particular area, the importance of that area is to be considered. Importance in the sense, that means if the peripheral area, say peripheral area of a particular city or town also, which is less important, even if it is say flooded, and it takes time to some time to get that the flood or the water discharges and water that means cleared from that area, some time will be taken. But if it is commercially important, right, commercially, that's to say hub of a city, there actually you cannot allow the flood to occur, frequent flooding also, right, frequent flooding that you cannot allow. And this actually, you see that because the cost factor is there, if you have got that over a long time, what is the maximum flow, say once in 100 years or 10 years if you consider, then a very large storm, right, which might have occurred or has occurred in previous years or so. So if you consider that once in 10 years I will capture or I will design for that, then your sewer, this size will be much bigger also. That will be uneconomical also. Right. So when that the cost will be considered, then you cannot take simply that for longer duration the what is the maximum or largest runoff also which we have experienced. This is one part. Another part is that importance of the area. If a particular area is not allowed to have flood frequently also, then in that case you can have that accordingly, that what flood or duration you will consider. Now manual says that for peripheral area, let me write here over here, the methods that will be discussed in more details later. So here this also I am erasing. So this is for the storm frequency. Storm frequency. So that is actually for residential area. Residential area. So that is considered twice residential, and that means let me just erase this. This one, that is one is the peripheral areas, so that is twice a year. Central and comparatively high priced area, central and say high priced area where the frequency of flooding should be less. Here, if the frequency of flood is more flooding, then it does not matter much, but here it matters. So here, once in a year, you consider. Okay, so here the volume of, or you can say the storm frequency, that means this that storm amount, that would be lesser. But here, once in a year, that would be capturing the larger this flow also. Similarly, commercial and high priced, that one. This is high priced. Let me just change this one. Commercial, central and comparatively high price, or comparatively important area, say. Important area. Let me just change this one, because another is there is a commercial and high priced, because this is categorized here for this commercial or institutional area also. This would be once in 2 years. This is very important, because you see that, as I have told, that this once in 2 years, that means a larger storm which has occurred, or which the probability to occur once in 2 years will be more than once in a year or so, and it would be further more than twice a year or so. Right? So today we will, go to this extent only. That is the storm frequency, how we will, take on what basis and consideration. So one point is remember, economy, very important thing. Right? So you cannot afford a very, high cost, very expensive system, stormwater drainage system also for a particular area. Though maybe, even though it is very, important also. Right? You cannot have the once in 10 years flood you will consider. And unnecessarily, bigger diameter also that is to be provided, for which the cost will be more. On the other side, you cannot, let the very important areas, high-priced areas, commercial, institutional, and all these, to be flooded very frequently. That also you have to consider. So, considering these two major parameters, we in fact decide that what would be the storm frequency or so. Accordingly, we have to proceed for the design also, and these are discussed and delineated in the CPHO manual also, that what are the basis, as well as what would be the bearing of this for the design of the storm drainage system. So friends, let us wind up here. Let us end up here for that estimation of storm runoff, and more or less the design of storm drainage system. So we have considered the design of sanitary sewerage system and the storm drainage system separately also. And while doing that, estimation of flow is important. That is why we have discussed this. So let us sort of end up here. So you may just close this. Okay.
Thank you.
Thank you, Sohini, for your this patient system management.